Hey folks, it's Mr. Ray here with our next lesson in grade 12 vectors. Today we're going to be looking specifically at R2, so two-dimensional space using just x and y coordinates. We're going to be looking at algebraic operations in R2. And compared to working things out graphically or geometrically with vectors, a lot of people prefer the algebraic approach. Instead of drawing things out, you can actually use algebra. So we're going to be working with representing vectors in two forms. We're going to be looking at standard basis vectors, and we're going to be looking at component vectors. So we'll look at the definitions of these in a second, but I'll show you both approaches for several questions. I think eventually most people will prefer the component vectors. They're just a little more, little less detailed and just number based. So that's probably the direction we're going in, but it's important to understand both ways of representing vectors. Okay. So the key concepts in R2, I believe we talked about this before. We have two unit vectors. We have vector I hat, which is basically the unit vector, has a magnitude of 1 along the x-axis. And we have the j hat vector, which is the unit vector along the y-axis. And we're going to use these multiples of these two vectors to represent any vector in R2. So if we have a position vector, basically from the origin to the point, so vector OP, we can either represent it as the components of the vector, or we could represent it as multiples of the unit vectors. So A and B here are scalar multiples of the two vectors I and j, and they can actually create any vector in R2. You can see the relationship between the component vector. Component vectors doesn't have to represent things in terms of I and j. It's just got this is the x component and this is the y component. So these numbers are the same for both representations. And in order to get the magnitude of the vector, we still do the same formula based on Pythagorean theorem. We take the sum of the a squared and b squared and take the square root. That gives us the magnitude of the vector, of the position vector. Okay, if we have two vectors, if we have 2 points, A and B, and we have a vector between these 2 points, so it starts at A and goes to B. I'll show you where this comes from. I know it can be confusing at first, but if you want to get vector AB, you take vector OB and you subtract vector OA. I'll show you where this comes from, but basically will be, once we know these components for OB and OA, which are the position vectors for OB and OA, we will just subtract their components to get the resultant components. And we'll do plenty of examples of that. The vector AB is equivalent to the position vector OP, since their direction and magnitude are the same. So yeah, we'll get to that as well. But the position vector, so AB is from A to B. Position vector is from O to P, and we're going to show that the magnitude of AB is the same as the position vector. Okay, this is from the textbook. So position vector OP, this is showing graphically what we're doing. If we have a point P on our R2 space, our XY grid, there's our point P, there's our O, stands for origin, so the position vector always goes from origin to the point. If I want to represent that vector OP in terms of components, I can say it's going to in terms of I hat, which is the unit vector here, I can say it's a multiple of I plus a multiple of j together. That gives me, if I add those together, I get the vector OP. Okay. Now we call I and j standard basis vectors because they're kind of the building blocks of creating any other vector. So it's basically the unit vectors in direction x, unit direction and vector y, which are I and j. If we combine scalar multiples of those two, we can create any other vector. So we've already mentioned that before, but graphically this is how it's represented. Okay, so want a little bit of practice going back and forth between using the component form, which is probably what we'll be using most, and the unit vectors I and j. So here we have position vectors OP and OQ. We've got the component form of them, and what we want to do is create the rewrite these equations in terms of the unit vectors. So this is pretty straightforward. So vector OP, so we can tell from that first number that's kind of the multiple of the I vector, which is the unit vector along the x-axis. So I can represent that as 1 times I hat, or just I hat, and then plus 2 times j hat, because that's the, sorry, those are the multiples of I and j respectively. Okay, and similarly for OQ, that's -3 times I hat, so -3 I hat. And since there's a 0 there, 0 times j hat is nothing. Basically, that would be the 0 vector, so we can just leave that as it is. Okay, now let's do the opposite approach. Here are some vectors OA and OB in standard unit vector form. So I want to rewrite those in component form. This is much easier. I can ignore the j's. So this one here, this one's a little bit, you have to be careful with this because it's not just, it's not just one number that goes here. It's always the basically the scalar multiple for I, comma, scalar multiple for j. Well, the scalar multiple for I, since there's nothing there, is 0. And scalar multiple for j would be -1. So make sure you've always got 2 values in here for R2. And then for OB, we've got scalar multiple of 5 for I, so that 5 goes in the first position. Scalar multiple for j is -4, so it goes there. So that just shows you going back and forth between unit vectors and component form, how that works and how they are related to each other. Okay, this example here, addition and vectors using component form. Using vectors A equals 1, 3, and remember these square brackets represent vector components now. So that blue vector, that's our A. Let me try to put it there, and this would be our B. Okay, so we're going to actually want to, and you can see the relationship there. So A is basically showing we go positive 1 unit in the x direction and positive 3 in the y. So that vector A, you can see the relationship. Vector B, it's a multiple of 4 in the x direction, multiple of 2 in the y direction, and we get that red vector there. So let's see what I'm doing here. So if I want to add A plus B, and I want to do A minus B, and I want to show 3 times A. So let's try that out. So remember from the first couple of lessons, I can just make my parallelogram I can recreate B over here. So if I wanted to redraw B, so 1, 2, 3, 4, 1, 2. So if I went from here to here, the tip of the head of A up to this point, that vector has the same components as B, so it really is B. And if I connected those, you could see, well, that's got the same components as A. And if I add those together, if I go from, well, either way, A plus B or B plus A, just go straight up the middle here, that vector there will be A plus B. Let me just zoom in so you can see that better. Okay, so we've got A and B here a couple of times, and then A plus B is formed by combining the vectors. Now, if I did negative B, so if I want to do A minus B, well, there's A. Now, if I redrew A so that the direction was opposite, so basically it would be -4, -2 for the components. Let's see, I go 4. So let me get this right. 4 to the left and 2 down. So this vector here, and when you put negative B and positive B together, it should look like it's parallel, or at least in the same line. So this would be negative B. Okay, and now I can actually, using my graph, I can add A and negative B, which is the same as A minus B. So that would be connecting these two up. So that would be A minus B there. Now 3A, I don't think I can fit that on here, but if I were to try, I would basically extend this. This would be a scalar multiple of A, so it's basically 3 times as long, so it would go up to there, that would be 2, and up to here would be 3A, something like that. But it's off the graph, so I'll just leave it to your imagination what that would look like. Okay, so that's the graphical way of, figuring out what this is. I could actually tell you that the components of A minus B, based on the position vector here, that would be -3, 1. Okay, and I could tell you that A plus B would be, that would be up to 5, so 5, 5. So A plus B would be 5, 5. A minus B would be -3, 1. Let's try it using our component vectors. Okay, so you'll see that it's much more approachable than doing it with a graph. You certainly don't want to do the graph approach every time, but it's nice to be able to compare them and show that, first of all, that this approach is right, but how they relate to each other. Now, if I wrote the components of A, which I know they're given, 1, 3, and I add that to the components of B because of the add sign there, 4, 2. This is as easy as it might look. We just add the X components together to get our result, so that'd be 5, and we add our Y components together, that would be 5 as well. And if you remember, that's what I said A plus B was, it's 5, 5, if you add up the displacement horizontally and vertically. Okay, let's try A minus B, see if it equals what we thought it would from the graph. So this time it's 1, 3 minus 4, 2. So this time we're subtracting the components. So 1 minus 4, -3, and 3 minus 2 is 1. And if you remember, that's what I said this was, -3, +1. Okay, and then 3A. This time we're actually doing a multiple of the components. So 3 times, so we're doing A, 1, 3. So again, it works like you think it would. Algebraically, multiply each of the components by 3, we get new components vector of 3, 9, and that would be what you know, if we had this graph extended, that point at the end there would be at coordinate 3, 9. Okay, so that shows you how we do addition, subtraction, and multiplication using component form. It's as easy as you would hope it would be. Okay, so let's zoom back out a bit. Okay, so example 3, vectors defined by 2 points. So I told you we'd come back to this. So not all your vectors always start at the origin. So this example, we've got 2 points A and B, and notice this time the brackets are round. That's just showing their coordinates. That's not an actual vector. So I've got my point at 1, 3, that's my A. And I've got a point at 4, 1, that's my B coordinate. And I'm just going to draw straight lines from the origin to both of those points. And also between them. So basically forming a triangle between A, B, and the origin. Okay, now remember the position vectors are from the origin to the point. So I've got a position vector there, OA. I've got a position vector here, OB. And then I've got my vector AB because it's asking to draw the vector AB. So the direction would be from A to B. Okay, so you see the direction, they're important. So OA goes that way, OB goes that way, AB goes that way. So I'll actually label this as AB. And well, you know this is OB and OA. So if I want to represent AB, okay, I can actually use this triangle to show how we get from A to B instead of directly from A to B through the origin. So if I was to write that direction, basically I'm starting at A and I'm going to O. So that would be a vector AO. And then I would add vector OB. Okay, so I'm basically going from A to B through the origin in that direction. Okay. Now, if I look at my inventory here, what do I know? Well, I know OB. I've got OB here. But AO, I've actually got vector OA, not AO. But you know that AO and OA are just opposite direction, and I can switch this, I can change this to OA if I put a negative sign in front. So vector AO is negative vector OA. Just because I actually know what OA is and I actually know what OB is. Now I'm just going to change the order of this because it's nicer to start with positive and then subtract instead of the other way around. So I'm switching this over to OB minus OA. And this is the important, you're going to be using this a lot. If you want to get the components of a vector between 2 points that don't include the origin, which is most of the time, this is going to be your formula. So the vector AB is the position vector OB minus the position vector OA. So let's try that out. So now we can actually plug these in. We know that OB, well, we didn't write this down yet, but OB is 4, 1. And then we're subtracting OA. So OA, that goes right 1, up 3. So that's position or component vector 1, 3. And again, just like we did on the previous example, we subtract the x components with the y components. So that would be 4 minus 1 is 3, and 1 minus 3 is negative 2. And you can see that if I travel from A to B, I go to the right 3 and I go down 2, and that's reflected in its components. Okay, so that's a really important example because you're going to be doing that quite a bit. Okay, let's try something different. And this is kind of a new perspective of trigonometry using vectors. So we have these 3 points. You can see the round brackets, 3 points in R2, and 3 points will create a triangle, triangle ABC. So we're going to use our new vector math. We're going to calculate the value of, the magnitude or length of AB plus the length of BC plus the length of CA. Those are the 3 sides. If we add those together, that's the perimeter of the triangle. And then we're going to do something else here, AB plus BC, magnitude. Okay, so this is going to require a little bit of time. So using what we just did, we know that vector AB, actually before we do that, we're actually going to turn these points into position vectors. So if I have a position vector OA, it's basically going from the origin to point A. Well, the components are exactly the same as the coordinates. So the position vector OA will have components -3, 7. The position vector OB will have, no big surprise, components 5, 22. And finally OC will have components 8, 18. So now we're working with components or vectors instead of coordinates on the XY grid. Okay, so if I want AB, remember the formula for this. This is going to be OB minus OA. And luckily we've just created those, so that's going to be 522 minus OA, which is -3, 7. Okay, if we combine those together, we're subtracting. So 5 minus -3 is 5 plus 3, which is 8. And then 22 minus 7, 15. So that's the vector components for AB. We're going to do the same thing for the other 2 sides. So BC is going to be OC minus OB. Just remember, you have to switch the order around, right? You probably think, well, should I put OB minus OC? Well, I showed you on this previous example why you don't do that. So make sure you get the order right here. Otherwise what happens is your components are the wrong signs. Okay, so don't do that. So OC, we have 8, 18. We subtract OB, which was 522. We get 8 minus 5 is 3. 18 minus 22 is -4. And then the last side, we want CA. So CA would be OA minus OC. Okay, OA was -3, 7. Subtract OC, 8, 18. So -3 minus 8, -11. And 7 minus 18, also -11. Okay, so we have actually got the vectors components for all 3 of the sides. What we want to do is get the length of these 3 vectors. So that is basically using Pythagorean theorem based on the components. So you could consider this to be the 2 non-hypotenuse sides of a triangle. So if I want to get the 3rd side, well, that's going to be square root of basically each of these sides squared, added together. So AB is 8 squared plus 15 squared, square root, and that's equal to 17. Magnitude or length of BC is going to be equal to square root of 3 squared plus, not square root, yeah, square root of 3 squared plus negative 4 squared. That works out to 5. And then CA is equal to square root of negative 11 squared plus negative 11 squared. And that works out to approximately, this one you have to round, 15.6. Now we don't know the units, so you could either just leave it like that or put the word units. Now I've got all three of these values, so all I have to do is the perimeter of ABC is the sum of these three things. So magnitude of AB plus magnitude of BC, not BG, plus magnitude of CA. So that's equal to 17 plus 5 plus 15.6 equal to 37.6 units. So that's the perimeter of that triangle. So kind of an interesting way of, the math seems pretty simple, but really a different way of getting it than we did in trigonometry or earlier on before we did trig. Okay, so part B says calculate the value of the magnitude of vector AB plus BC. Okay, so first of all, we're going to get the components of this combined vector AB plus BC. So AB plus BC. Well, we know from before, if I'm basically going through B to get from A to C, so the end result is the vector AC. Okay, now I don't have the magnitude. I don't have anything about AC, but I do have something about CA. Now CA and AC are, these vectors will have the same magnitude but opposite direction. Okay, so I could just call vector AC, I can just call it negative vector CA. And I know what that is. I've got the components for CA. So I can basically apply a negative multiplier to those components that I already had for CA. So negative 11, negative 11. If I basically multiply both of these by negative 1, I'm getting 11, 11. Okay, and then therefore the magnitude of AB plus BC is really the magnitude of, well, this one or this one, which is going to be square root of 11 squared plus 11 squared, and that's equal to 15.6 approximately. And if you notice, those two values exactly the same, and they should be, because the magnitude of CA and AC should be the same because they're the same length, and that's what magnitude is measuring. Okay, so a little exercise in using algebra to solve a problem. Okay, one last question. This should be fairly quick. Okay, for the vectors x equals 2i plus 3j and y equals negative 4i minus 3j, determine the magnitude of x plus y vectors and the magnitude of x minus y vectors using two methods, component form and standard unit vectors. So eventually, you just choose one of these methods, but I want to show you both approaches just so you have exposure to two ways of doing the same question. So we'll do the component form first. So I've got x equals, Now if I change vector x into components, that would be 2, 3. And similarly y, vector y would be -4, -3. And so if I want to add these two vectors, I'm just going to add their components. So 2, 3 plus -4, -3. So that's really just adding the components. So that's -2, 0. And the magnitude of that is really, using that again in our Pythagorean theorem. So it's a square root of basically -2 squared plus 0 squared, which is square root of 4, which is just 2. Okay, so we've got x plus y's magnitude there. Let's do x minus y. So this time we're subtracting. Okay, so 2 minus -4 is 2 plus 4. 3 minus -3 is 3 plus 3. So 6, 6 is our component result. And if I want to do the magnitude of that vector, again, it's going to be square root of 6 squared plus 6 squared, 36 plus 36. So square root of 72. And I can reduce that to 6 root 2, simplified. The way that's done is I can, change root 72 to root 36 times root 2. Root 36 is just 6. Okay, so that's how we do it with components. With standard unit vectors, using the I and the J's. Okay, so I've already got them written in terms of standard unit vectors. I don't have to convert them. So if I just write this out, I've got x plus y is equal to 2i hat plus 3j hat. And I'm adding those components as well, minus 4i hat minus 3j hat. So if I simplify those, I could combine the I hats and j hats. I've got -2i hat and the 3j hat, -3j hat cancel each other out. So I'm just left with -2i hat as my result. And then if I want to do the magnitude of that, vectors x plus vector y, that's going to be, again, I do it the same way I did above. So it's going to be square root of -2 squared plus 0 squared, which is square root of 4, which is also equal to 2. Take some of that radical off. Okay, and you can see that matches up with what we got. You can also see the comparison of the resultant vector, x plus y. You can see I've got the -2 that goes with the I, 0 for j hat. Okay, do the same subtraction this time. So now I've got 2i hat plus 3j hat. And now I'm subtracting these, so they turn into additions. So plus 4i hat plus 3j hat equals 2i hat plus 4i hat is 6i hat. And then 3j hat plus 3j hat is 6j hat. That's it. And then the magnitude of that vector, x minus y magnitude, is equal to the square root of 6 squared plus 6 squared, that's 36, 36, 72. And again, you see the exact same result as we just did with just looking at the components. So I think most people, well, my experience is pretty much everybody prefers this method because you don't have the clutter of the i's and the j's all over the place. You're just really working with numbers. So, but you are expected to understand both methods. Okay, so that's it for today. I've got some homework for you to practice this with. And the next lesson will be similar to what we just did, except instead of looking at R2, we'll be extending into R3. So how do we do algebraic operations with vectors in R3? So until then, have a great day, and we'll see you then.